Okay, welcome to another physics problem solving session here. This time we're going to do a problem involving acceleration. So this is the deer problem that we talked about in class. Okay, the only time I've ever come close to hitting a deer was when I was in a strange land called Kentucky. I was driving through Kentucky one night and a deer leaped out in front of me. I fortunately didn't hit it. So I see a deer 30 meters ahead of me when I'm traveling along at 17.9 meters per second. Stomping on my brakes makes an acceleration of negative 5.90 meters per second per second. And the three things I'm asked to find is what is delta x to stop, how close do I get to the deer, and what time delta t was required to stop. Okay? So, as always, there are good strategies to follow when you're solving problems. The things that I always advocate that you do is you first draw a picture and then you write out your kinematic tables. So let's go ahead and draw a picture. So I'm cruising along in my Yugo, and up ahead of me was a deer. Okay. Now, as always, I have to make some choices here. And the choices I make are, what are my coordinates? In this case, this is a one-dimensional problem, so I only have to choose one coordinate. And which direction is positive? And where is the origin? So I'm going to choose the origin to be where I am at x equal to 0. I'm going to choose the positive x direction to be in the direction of the deer. And the deer, we're told in the problem, is 30 meters away from me at the moment that the problem starts. Okay, so I'm going to write out my kinematic table here. So in kinematics involving acceleration, there are 6 variables in our kinematic table. There is my final position, my initial position, my final speed, my initial speed, the acceleration, and the time involved. Now, as always, there are certain things that are told to you in the problem and certain things that you have to deduce or decide based on what you're told. Okay, so I've set up my coordinates, and so I've assigned my initial position to be 0 meters. Okay. Now, the deer is at 30 meters, but I'm not actually asked where the deer is. What I'm asked is, how far is it that I travel before I stop? So my final position is unknown. In fact, it's one of those things that I'm asked to find. My final speed, v, is something that I deduce from the problem statement. The problem's about me coming to rest. It doesn't say my final speed is 0, but based on the problem statement, I assume my final speed is 0. So we'll assume that my final speed is 0 meters per second. And my initial speed, we're told, is 17.9 meters per second. Now, my acceleration is told to me as a negative number. We're told that it's minus 5.90 meters per second squared. Now, this statement is made with a certain assumption in mind, an assumption that you and I have already made, namely that I was traveling in the positive x direction, so my speed was positive, and so when I accelerate in the negative direction. I'm slowing down. Whenever you're speeding up, your acceleration and your speed have the same sign. But if you're slowing down, your acceleration and your speed have opposite signs. And that's the case here. I know I'm slowing down, so this has a negative sign compared to my speed. So that's good. Finally, the time. That's something that we're asked to find. Okay, so my kinematic table is full up. I think it's good practice to write out your kinematic equations so you can stare at them when you are getting ready to solve problems. And the three kinematic equations that we use are x is equal to x naught plus v naught t plus a half at squared. V is equal to v naught plus at. And lastly, v squared is equal to v naught squared plus 2a delta x. Now, the easiest way to figure out what to do when you're trying to solve problems is to look at what you're asked to find and then find an equation that has everything known except that one thing that you're asked to find. Now in this case, the very first thing we're asked to find is what is delta x to stop? What is the final position in essence? Okay, so let's look at the first kinematic equation. The final position is what that kinematic equation is all about, and I'm actually don't know that. I know my initial position, I know my initial speed, I don't know time. So automatically this becomes an equation that's going to be difficult because there are two unknowns, x and t. Okay, I know a half, I know acceleration, and again I don't know time. Okay, so if we could figure out time some way, we could come back and use that problem. But let's go on for a minute. Okay, let's look at this second equation. Final speed, yep, I know that. Initial speed, yep, I know that. A, yep, I know that. And time, I don't know that. So this equation, I could solve for time, and I could put it back into the first equation and find the thing that I need to know, namely, what is the final position. Let's look at the last equation first, though. Okay, v squared, do I know v? Yep, I know v squared. V naught squared, do I know v naught? Yep. 2, I know. A, I know. And delta x is a combination. It's x minus x naught, one of which I know and one of which I don't. So this equation is also a very good equation because it involves everything is known except for one thing, the thing that we're asked to find, x in this case. So I'm actually going to use this equation, okay? So I'm going to take that equation, and my final speed, v, is 0 meters per second. So I'm going to set it to 0 right away so I don't have to carry around the extra v. V naught squared plus 2a delta x. And I'm going to solve this for delta x. So the first thing I'm going to do is I'm going to move this over to this side of the equation. So I have minus 2a delta x is equal to v naught squared. Delta x is equal to minus v naught squared over 2a. So that is the final position. Okay, this is my final position minus my initial position, but my initial position is 0, as we wrote in the kinematic table up here. So that's good. So I can evaluate this numerically then. I can just put in the values. My initial speed is 17.9 meters per second. That whole quantity is squared. There's a minus sign out in front. Over 2 times my acceleration, which is minus 5.90 meters per second squared. And if I punch that all into my calculator, the 2 minus signs cancel out, giving me positive. That's good because I moved towards positive x. And the end result is 27 meters. So I almost hit the deer, but I stop 3 meters before I actually get to him. Good job. Okay, now, the second question is, how close do I get to the deer? Well, that's pretty easy, right? The distance from the deer is my final position and the deer's final position subtracted from each other. So the distance is x deer minus my final position, which is 30 meters minus 27 meters, or 3 meters, as we just said. And then lastly, I'm asked to find what is the amount of time it took me to stop. And we remember from when we were looking at our kinematic equations up here, in this second one, I knew everything except t in this equation. I know my final speed, it's 0. I know my initial speed, I know my acceleration, and so I can find time. So let's go ahead and use that kinematic equation to find time. So that is v, which I know is 0. My final speed is 0, so I'm going to set it to 0, is equal to v naught plus a times t. I'm going to move that over to this side of the equation. So I have minus at is equal to v naught, or solving for t, t is equal to minus v naught over a. So this is the amount of time it took me to stop. And again, I can numerically evaluate that by simply substituting in values from my kinematic table. So there's a leading minus sign. My initial speed is 17.9 meters per second. My acceleration is minus 5.90 meters per second per second. The minus signs will cancel and give me a positive sign. The meters per second will cancel out one of these meters per second, leave me 1 over a second, which is seconds. That's good. I'm left with seconds, which is a unit of time. So if I evaluate that, I find that my stopping time is 3.0 seconds. Okay? So that's that whole problem solved from beginning to end. Now, I chose to solve this problem in a particular way by using this kinematic equation, v squared, first. You could have just as easily solved the problem for time first. That's what you were asked to find in part C. And then use that information to go back and solve part A. You will get exactly the same answer that I got here, and it doesn't matter that you solved the problem that way. It's your choice. In the end, we all get the same answer. Okay? So go home and practice that one, and I'll talk to you again next time.